We are discussing about the assumptions of the linear programming. The first assumption is related to the proportionality, which is imposed on the objective function as well as on the functional constraint. And as per the proportionality assumption, that contribution of each activity is proportional to the level of activity. Obviously, this is must for LPP. If this condition is not being imposed, then there will be a major problem with LPP. Means if this condition is not imposed, then we don't have the linear programming aspect. Then we have non-linear programming. Means it won't remain as linear. The second assumption is related to additivity. Again, it has been discussed. This is related to the total things. So this is imposed on the objective function as well as on the left-hand side of the functional constant. This says that a total contribution of all activity is the sum. Sum means simply the addition or subtraction of individual contribution of the respective activities. Means it rules out cross product term. Means if this is a case where the decision variables are multiplied, so they are the cross product term. So obviously here the degree would be 1 and 1. So the degree would be 2 and it would be non-linear. It would become non-linear. So the proportionality constraint does not rule out cross product term. So we have to rule out the cross product sum. So accordingly, we have the second constraint that is known as second assumption that is known as additivity. Means the total contribution either in the objective function or in the constraint should be an addition or subtraction of the individual contribution. Just like we have discussed in the objective function, this is the individual contribution of tables. It is the individual contribution of manufacturing of chair, and the total contribution is simply the addition. In the same manner, when we consider the left-hand side of the functional constraint, this is the total contribution for the wood utilization by the table. This is the individual contribution by the chairs, and for the total contribution of entire activity, we have to sum. Means we don't multiply the things. So this is not the case. So the total contribution of activities is the sum of individual contribution of respective activities. It rules out cross product terms. Now these are the two assumptions. This again, this assumption is must. If this assumption is not being fulfilled, right? If it is not fulfilled, then we have non-linear programming. We have NLP. Then we move to other assumption. The next assumption is related to divisibility. This is imposed on the decision variables. While we mention the decision variables, that is xj, we don't impose any condition. Means xj can have any value. Means any value means they can be integers and they can be non-integers also. Right? Means they can have any value, means they are divisible in nature. So this condition is imposed on the variables. So the variables are allowed to have any values, including non-integers also. Right? Now this condition is not must, right? Because in integer programming, which is a part of LPP, with some additional restrictions. So here the restriction is divisibility assumptions does not hold. Means in that case we impose the restriction. We impose the restriction that xij can take only integers value, or they can have only binary values, right? So this in that case it is divisibility condition has not been employed in the full sense. But even then, our model remains LPP. So integer programming is a part of LPP only. Now the last assumption is related to certainty. It is related to the parameters that are used in the model. In the model, we use parameters CJs. They are the objective function coefficients, like the profit amounts in our case. Then we have input-output coefficients, AIJs, right? That we have used for the different constraints, like for wood, paint, labor, etc. So these are the AIJs. And the third and the last one are the limitations that are imposed on our functional constraint. They are the BIs. They are the three parameters. One is the CJs. They are the objective functions coefficients. Other AIJs are input output coefficients. And the last one are the limitations imposed on the system. So it is related to the parameters of the model. So as certainties, the assumption of certainty says that values assigned to each parameter of the LPP, whether it is CJ, AIJ, or BI, are assumed to be known constant. The first thing is they should be known and they should remain fairly constant. Now, this assumption we use for the LPP, but we also consider that there are some variants also. The first variant is related to the sensitivity analysis. Sensitivity analysis is used when we examine degree of uncertainty for the parameter. Since the real life situations are dynamic in nature, so we consider their impact on our solution also. So in sensitivity, we try for different values of this objective function coefficient. But when we solve this model, then for a particular solving, they remains known as well as remains constant. And there are two other programming also. One is stochastic programming, other is chance constraint programming. Here, the level of uncertainty is very high. In this case, if in our decision-making situation, level of uncertainty is very high. So in that situation, we consider parameters are treated as random variables. Means these coefficients that are taken to be constant are taken as random variable. So this is the this case is known as stochastic or chance constraint programming that we are not considering in this situation. So these are the assumptions. These are the four assumptions: proportionality, additivity, and divisibility. And the fourth one is the certainty assumptions. Among these assumptions, the first two assumptions are paramount in nature, means they are must for the LPP. And in divisibility, for a particular case, they are assumed to be taken care of, but we can also consider their variance also. So this is the assumptions related to this thing. Now we have mentioned the general LPP form. We have used the general LPP form just like in the previous slide. Here the general LPP form. This is the general LPP. This is the general LPP form that we have used. Now we convert for the future purposes, we convert it into matrix notations. So here decision variables are X. So we are considering the decision variable vector, that is X is actually X1, X2 going up to Xn of the order n cross 1. The dimensionality are n cross 1. So this is the decision variable vector. So this is our vector, decision variable vector, that is X. Then we have objective function coefficient vector. This is C1, C2 up to Cn. Right? So this is are having order 1 cross n. Right? And this is the second vector. Now the third vector is again the the limitations that are imposed on the constraint. They are the B vector. So here the B vector is B1, B2, this is B, B1, B2 up to Bm. The order is again M cross 1. So this is the B vector. And here we have an input-output matrix also. So input-output matrix A is A11 up to A1n. Then we have A21, A22 up to A2n. And the last is AM1, AM2 up to AMN. So this matrix is of order M cross n, which are elements as AIJs. Right? Let me show you. Right? So this is the A matrix. From this, we have developed the A matrix. Right? This is the A matrix. So in the matrix form, we can write our general LPP form is here. Our purpose is determine the X factor, means we want to determine the decision variable X1, X2, Xn. Then it is Z is actually we have C1, C2, Cn, right? And this is the matrix multiplication of X1, X2 up to Xn, right? So here the order is 1 cross n. Here the order or dimensionality is n cross n. So this will be having a linear function, linear value that will be 1 cross 1. This is optimized, means either it is maximized or minimized. Then we make subject to the constraint. Then we here we use A matrix and multiply it by, let me write it here. Here we have A11, A12 up to A1n. Then we have A21, A22, A2n, and finally we have AM1 going up to AMN. So it is having the order M cross n. Here the order or the dimensionality is M cross n. Here we multiply it by the X factor, that is X1, X2 up to Xn. So here the order is n cross 1. And when we multiply, then obviously this product, here the order is m cross n, and here the order is n cross 1, and here the order of B is m cross n. So it can be written in this manner, right? So this is the way by which a matrix notations can be there, right? So let me use the whiteboard to explain this concept in a better manner. So here, the first one is we determine X factor, where the X factor is actually X1, X2 going up to Xn of the order n cross 1. Then we have objective function as optimize Z, which is actually C vector multiplied with X vector, that is C1, C2 going up to Cn, having order 1 cross n. Then we have X1, X2 up to Xn of order n cross 1, and the order would be 1 cross 1 for Z. And then we have subject to constraints. Here we have AX less than equals to greater than B. Yeah, the order of A is m cross n, order for X is n cross 1, right? n cross 1, and order for P is obviously m cross 1. So here we have input output coefficient matrix, that is A11, A12 going up to A1n. Then we have A21, A22 going up to A2n. And finally we have AM1, AM2 going up to AMN. Right? So this is our A matrix of order m cross n. Next is X vector, X1, X2 up to Xn. This is of order n cross 1, and we have greater than, equals to, or less than, right? And the multiplication, if we multiply A and X, the resulting matrix will be in dimensionality or order of m cross 1. So here it will be compared with B1, B2 up to Bm, and having order m cross 1. So these are the functional constraints. Functional constraint. And finally, we have non-negative restrictions also. Non-negative restrictions are x1, x2 up to xn, right, should be greater than or equals to 0, 0 up to 0. Means X matrix, X vector should be greater than or equals to the 0 vector. Right? So this is this concept has been used here. This is our model. Right? So this is the matrix form that we have discussed in this case. This is the matrix form in this case. So here the model has been developed. Now the question arises how this matrix or this model should be solved. So now we are discussing solution of linear programming problem. Right? Here, three approaches, three broad category of approaches are there. Means more than there are n number of cases, n number of approaches there. The first approach is related to the graphical method, where we try to develop a graph. Then the second method is known as simplex, where we use algebraic method. And the other one are also developed from the simplex method with some variation, like dual simplex, parametric linear programming, upper bound technique, and interior point algorithm. Now, in these two lectures, we will discuss these two approaches, that is the graphical method, and the next one are the simplex method. Graphical method has a very important limitations, that since we try to have a solution through a graph, so we will have only two variable cases there that can be solved using a graphical method. So graphical method can be used only for that situation where we have two variables or where we have two-dimensional problem is there. But if number of variables or number of dimensions are more than two, then obviously graphical method cannot be imposed, cannot be used. So in that case, we use simplex method, which is useful for any type of situations. Fine. So that will be our main method. But just to develop the concept, we will discuss what do we mean by graphical method. So now we will discuss the basic concepts of the graphical method. Right? So before discussing this concept, let us take an example and then try to solve it using a graph. Okay. I'm explaining the graphical method. First, we discuss a practical situation, then we will have the concept formation from it, right? Then finally, we will take the case also that we have taken up. So just I am taking a simple example to develop the concept. Here the problem that we are taking up is like that. We have to maximize the objective function, and the objective function is 3x1 plus 4x2. Obviously, we try to determine x1 and x2. We want to maximize this, right? It is subject to the constraints. The constraints are 4x1 plus 2x2, that is less than or equals to. And just to remind, this is a very simple example. We will take up more examples also. And x1, x2 are greater than or equals to 0. So this is our objective function. This is our objective functions, right? And these are the constraints or restrictions that are imposed. Now we try to find out the value of x1 and x2. Means we try to solve this linear programming problem using graphical method. As we have, we are using a two-dimensional graph here. So here we have two-dimensional graph. Here we have a variable x1 on x-axis and another variable x2 on the y-axis, right? We are using graph. Now, since they represents the line or the plane, so we try to represent that. So here the first equation is, function is 4x1 plus 2x2, that is less than or equals to 80. For the time being, we will have 4x1 plus 2x2. This is less equals to 80. For the time being, we are considering an 80. So this can be written as x1 divided by 20 plus x2 divided by 40 equals to 1. Right? So here we have we have intercept at x1 axis as 20 and intercept at x2 axis as 40. So here we have coefficients as coefficient as 20, 0, and the second one is 0, 40. So by this, a line can be drawn. Right? So this is the first case. This is the situation 20, 0 and 0, 40. Right? In the same manner, in the second equation, we will have 2x1. This is the first. This is the first. And in the second, we have 2x1 we have 2x1 plus 5x2 less than or equals to 180. So for the time being, we take it as 2x1 plus 5x2 equals to 180. And accordingly, we will have x1 divided by 90 plus x2 divided by 36 equals to 1. We have converted in this case, right? So here, the points, here the intercept on the x1 axis would be 90 and intercept on the x2 axis would be 36. And we have points as 90, 0, and the other one is 0, 36. Now we try to draw these lines on this graph. So we have something like that. Okay. And here also we will have 10, 20. And so on. Right? Here the first line, that is x1 upon 20 plus x2 upon 40 equals to 1. So this is our first point and this is our second point. So we draw a line from these two. Right? Suppose we have drawn a line from these two. We have drawn a line from these 2 points. Right? So this is our line number 1. And since this equation demands that the greater less than sign is there, so obviously for less than we try to consider this region. So this is the region that is satisfied if we consider this line. Obviously it will go beyond this coordinate, but we also have two conditions like x1 and x2 equals to 0. So let me denote this condition also, that is x1 and x2 greater than or equals to 0. So here we have x2 greater than or equals to 0, and here we will have x1 greater than or equals to 0. Means we are considering only this coordinate. Okay. So that's why we have not moved beyond this point. So this is the first condition that we have discussed. Now, first constraint that has been discussed. Now we will take up the second constraint. Now I am taking up the second constraint, that is x1 upon 90. So this is our second point, and other is x2 divided upon 30. So here again a line can be drawn through this surface. So here we have second line. This is line number 2, and this is again line number 2. And since we are considering the less than or equals to part, so we will have this is less than and this is less than part, right? So if we consider this part, so we will have, it is denoted by blue part. So this blue part is being satisfied by the line or the function 2 and constraint 2, and the green part is denoted satisfied by this. Now all these two constraints are paramount. So we will consider the common part. Now I am taking the common part of these two. So here the common part would be this part, or we will have a better color. So here the common part is this part. Okay, this is a common part. So this part is being satisfied by all the constraints. Satisfied by all the constraints. So all the constraints are satisfying this part. Okay. So this is satisfied by all the constraints, right? So if we consider this part, this is the part of our interest. So here it is 0, 0. Suppose this is O, this is A, this is 20, 0, and this is the point. This is a point that is satisfied both the lines. So the coefficient, so the values of these 2 points, by solving these two, we will have 2.5 and 35. You can solve these values. So this is 2.5 and 35. Okay. And this is the third, it is 0, 36. Right? So this is the space that is bounded by the constraint. Now, this space denotes our fulfillment of both all the constraints, means both type of constraint. So here it will have a solution. This part is known as solution space. This is known as solution space. Right? because it satisfies all the constraints. So here, obviously, if we consider this space, which consists of infinite number of points, so this is the space where both the constraints that are paramount in nature are satisfied. So it will be this part of the solutions that will be taken care of, right? Now, I am moving to our main slides to explain the concept, right? So here we obtain the feasible region. Here the feasible region is the collection of feasible solution for which all the constraints are satisfied. So we have developed this, right? Just like in our example, we have developed the feasible region. If the second point arises, obtaining of the optimum solution. So these feasible regions are developed using constraints and restrictions. And obviously, it is paramount in nature, means that has to be followed. And from this feasible region, we move to the second part, that is obtaining an optimal solution. A feasible solution that has most favorable value of the objective function, means where the objective function is mostly satisfied. So let me again share. Right? So this is the thing. Right? Here, this region is can be termed as the feasible region. This is our feasible region. Here our solution exists, right? So here we have infinite number of points, right? So where our solution exists. Now here we consider a concept that is known as corner point feasible solution, right? Corner point feasible solution means here we have corner points as 0, that is O, that is another corner point is A, next is B, and the third corner point is C. So we have corner points O, that is 0, 0. Other we have A is 20, 0. Then we have B is 2.5, 35. And the C, the last is C is 0, 36. These are the corner points that we are going to consider. So these are the, here, these are the corner points. Why corner points are considered? Why we consider the corner point solution? Right? For that we have to discuss some concepts or some assumptions or some concepts that are important. So this is the part that we will take up while we try to optimize, we try to find out the optimum value of our function. Thank you.